4.2 radian measurements. Okay, so today we have, so far, you have mostly been measuring, you measure distance using kilometers or meters, you can measure temperature using Celsius or Fahrenheit, and you measure angles using degrees. Well, today you learn how to use radians, which is a different angle measurement. It actually makes far more sense than using degrees because radians is based on the circumference of a circle involving pi. Everything is expressed based on pi, in terms of pi. So what you're going to do is you basically consider an equilateral triangle, which would look like this, right? All 60-degree angles in there. And you're basically just going to put your hand on one side and compress it, okay? You're just going to push down on one side of the triangle. So that's your first blank there. Push down on one side of the triangle until this right side bows out. Okay, so you haven't changed the length of any of the sides, but now you have 2 lines and an arc instead of 3 lines. Okay, so what you end up with, that diagram on the right, where you have your circle, and you have an angle drawn from the origin, O, and your initial arm is along the horizontal axis. It has a length of r, because it's a radius, and your terminal arm has a length of r, and this arc, okay, from, if we could extend these guys, don't need to really, but from here to here also has a length of r. Okay, the arc length is r as well. It's the same as the radius. Everything else is labeled on your diagrams, so we can take a few notes. 1 radian, this is for the lines there, 1 radian is the measure of an angle. 1 radian is the measure of an angle made at the center of the circle, at the center of a circle, by an arc along the circumference, by an arc along the circumference that is equal in length, to the radius of the circle. I'll read that again. 1 radian is the measure of an angle. So if we look at this diagram again, this is 1 radian made at the center of a circle. So you could do it on this circle as well. This is 1 radian, 1 rad, 1 rad is 1 radian. The angle is made at the center of a circle by an arc along the circumference that's equal in length to the radius of the circle. So if the arc length is r, then the angle made is 1 radian. Same thing here. If this is all equal, then this angle is 1 radian. Okay? That's how we measure it. And we're going to talk about what it is to go all the way around a circle. We're also going to talk about how to get from degrees to radians and how to get from radians to degrees.
Every degree has its own constant radian, right?
Okay, beside your next little diagram, you have a sentence that starts with the radian angle, the radian measure of an angle theta. So theta is some angle, and the radian measure of that angle is defined as the length of A A is the arc length. The length, let's say this, the length comma A of the arc that subtends, talk about that word in a second, that subtends the angle divided by the radius of the circle. Divided by the radius, comma, r, comma, of the circle. Okay, so in your diagram, which I can put over here, you have a radius drawn, okay? You have another arm drawn. You have an angle formed, and this length, so this is r, and this is theta. This length right here, this is the arc that subtends the angle. That's from here to here. This arc length is A. Okay? So no matter how big that angle is, the arc length is going to grow. Okay? So that is A. The length A, in the case where we're dealing with 1 radian, A is the same as R. But that's not always the case. That's only the case on one particular angle, 1 radian. But A is the arc that subtends the angle. So it's the distance between those two radius along the arc. Okay, good. So then the angle is measured as theta equals A over R. Okay, so if you do the length of the arc over the length of the radius, you will get the measure of angle theta in radians. Okay? Next note. For one complete revolution, the length of the arc, for one complete revolution, the length of the arc equals the circumference of the circle. For one complete rotation, the length of the arc equals the circumference of the circle, which is 2 pi r. Well, if we take our original equation here, that the measure of angle theta is equal to A over r, and we know that after one full rotation, the arc length is 2 pi r, then we're looking at a measure of angle theta that is 2 pi r over r. We can cross out our r's in the numerator and the denominator, and we get a formula that says that for one full revolution, the angle of theta is 2 pi. Okay? Can even add the units of measure here. This is 2 pi radians. That's the angle measurement for one full revolution. That means 2 pi radians equals 360 degrees. 2 pi radians equals 360 degrees. Okay, so the relationship between radians and degrees is that 2 pi radians is equal to 360 degrees. What you're actually going to do in those two boxes is change the first box. It shouldn't say relationship between radians and degrees. It should say converting from radians to degrees. And your next box is correct. It's degrees. It says converting between, but just change it to say degrees to radians. So when we're converting from radians to degrees, that means you have the degree, you have the radian measurement and you're trying to get the degree measurement. You have to remember that 2 pi radians is equal to 360 degrees. Well, let's divide both sides by 2 pi in order to get 1 radian, right? So if we divide both sides by 2 pi, then on the left we'll get 1 radian, and it'll be equal to 360 divided by 2 pi degrees. Well, 360 divided by 2 is 180. 180 over pi. That is 1 radian. Okay, so this is in degrees on the right-hand side. So basically, if you have the radian measurement, let's say you have 2 radians, you know the angle is 2 radians. Well, all you have to do is multiply 2 by 180 over pi, and you'll get the degree measure. Or you get pi radians, because radians are often expressed in terms of pi. So let's say you had pi radians, and you wanted to find out what that is in degrees. Well, you would take 180 divided by pi times pi. You'd end up with 180 degrees. Okay? So that's just one example. We'll use that a whole bunch. What about going from degrees to radians? Well, if 2 pi radians is 360 degrees, then 360 degrees is 2 pi radians. For each degree, if we want to know what just 1 degree is so that we can actually use it in our conversions, we need to divide both sides by 360. So 1 degree equals 2 pi over 360 radians. 2 divided by 360, I can reduce that to 1 over 180, which just leaves us with pi over 180. You say, well, that's a tiny number to take pi, which is 3.14, and divide it by 180. Well, yeah, it's a tiny sliver of the circle because it's only 1 degree. It's 1/360th of the circle, okay? This right here also lets us know that 1 radian is approximately 60 degrees. It's a little less than 60 degrees because we smushed that equilateral triangle, remember? But this is approximately 57.3 degrees. That's just helpful reference. You don't need to know that. In conversions, you'll be using these formulas appropriately rather than estimating. And then also helpful to know that 1 degree, what is pi divided by 180 actually? Well, it's about 0.0175. Okay, so it's a small number measured in radians. At the bottom of your book page there, you have a note that says exact angles in radians. Exact angles in radians are usually written in terms of pi, unless it is a whole number, but the special angles are not. They're all in terms of pi. Exact angles in radians are written in terms of pi. And for example, a straight line of 180 degrees is equal to, or is referred to as, simply pi. Okay? All the way around the circle is 2 pi, so halfway around the circle must be 1 pi. Let's do a couple of examples here. Example 1, you have converting degree measure 35 degrees into radians. So all you're going to do is take that, example 1a, 35 degrees, and find out what that is in radians. Well, 1 degree is pi over 180 radians. So if we want 35 degrees, we just need to multiply this side by 35, okay? So we end up with 35 degrees equals 35 times pi over 180, which gives us 35 pi over 180, which can be reduced because top and bottom are both divisible by at least 5. Give us 7 pi over 36. Okay, so 35 degrees is the same as 7 pi over 36. In example 2, we're going to do two different radian measures converting to degree measures. You'll notice in A, it's easy to tell that it's radians because it's in terms of pi. It's pi over 4. But in B, it's not in terms of pi, but it is still a radian measure, okay, even though it's 5.86. So you'll have to be mindful and wary to recognize when you're talking about radians and when you're talking about degrees. But to go from radians to degrees, I just use my formula. 1 radian is 180 over pi. So all I have to do then is multiply pi over 4 times 180 over pi. So pi over 4 times 180 over pi. My pi's cancel out. I have 180 over 4, which is 45. So we're looking at 45 degrees. Make sure you take your degree symbol with you along the way, okay? Otherwise, it doesn't make sense. You can't say that this times this. I suppose you can because this is really just 1. Anyway, take your degree sign with you. It's 45 degrees. B, we do the same thing with B, which is 5.86 radians. And you're going to take that 5.86 and multiply it by 180 over pi degrees, which in your calculator gets you approximately 335.8. So you can see that's quite a high number. That's almost a full revolution around the circle. And that makes sense because 1 full revolution would be 2 pi, which is about 6.28. So 5.8 is getting pretty close to 6.2 or 6.3. It's almost all the way around the circle. It's 335.8 out of the 360 degrees of a full revolution. Okay, our next example gets us to use our arc length formula. So we're given the arc length for, we're going to find the arc length for a given angle. So Suzette chooses to ride the camel on the carousel. Carousel goes round and round and round and round. The camel is located 9 meters from the center of the circle. So if we wanted to give ourselves a diagram to help us understand this, we'd look at the carousel from the top. We'd label the center. And we can assume that the carousel is maybe bigger than this. This is just going to be the path of the camel. And that is 9 meters. If the carousel turns through an angle of 5 pi over 6, so in order to think about my diagram, I'm thinking 5 pi over 6 is almost 1 full pi, which is almost halfway around this circle. So we're maybe looking somewhere over here. This angle right here is going to be 5 pi over 6. Determine the length of the arc traveled by the camel to the nearest tenth of a meter. So we're looking for the arc that subtends an angle of 5 pi over 6. Okay? So here we go. List the things that we know. We know the radius is 9. We know theta is 5 pi over 6. And we know that, and this is, you won't have to do this the whole time, but I'm going to write down kind of in words what we're looking at. The angle measure in radians is equal to the length of the arc that subtends the angle over the radius. So what do we have? We've got the angle measure in radians, theta, equals the length of the arc that subtends the angle, A, over R. Sub in the things that we know, or we can rearrange the formula first to express it in terms of A, which is what we want to find. So I can multiply both sides by R, and that would get me A by itself. Multiply both sides by R, I would end up with A equals R times theta. Well, we know that R is 9, and we know that theta is 5 pi over 6. So we have 9 times 5 pi divided by 6, which in our calculator gets us an arc length of approximately 23.6 meters. Okay, it's a pretty simple formula to apply. You just have to remember that it is one of the tools in your toolbox now and use it whenever appropriate. Again, you could use the formula to figure out R if you didn't know it, or theta if you didn't know theta. Angular velocity of a rotating object. The angular velocity of a rotating object, example 4, is the rate at which the central angle changes with respect to speed. So basically, if you had an angle rotating around and around and around and around, okay, that's the central angle. The terminal arm is going whipping around real fast. Okay, it rotates with respect to time. The hard disk in a personal computer, personal computers aren't really created with hard disks with moving parts anymore, but anyway, they used to rotate at 7,200 RPM, 7,200 revolutions per minute. So it would spin all the way around, one full revolution, 7,200 times every minute. And we want to take that measurement and determine its angular velocity in two different measurements. A, degrees per second, and B, radians per second. Okay, it's given in revolutions per minute, 7,200 revolutions. So we need to think about how many degrees are in one revolution, and then figure out converting from minutes to seconds, and in B, how many radians are in one revolution, and then converting from minutes to seconds as well. So first, A. Let's figure out how many degrees we're talking here. 7,200 revolutions. How many degrees in a revolution?
360.
360 degrees per revolution.
Divided by 60.
Gets you 2,592,000 revolutions in 1 minute. So to get that per second, we need to take that, let's say, angular velocity equals this big number, 2,592,000 per minute. Per is your dividing line. 1 minute, we're now going to convert into 60 seconds. And this is degrees. Sorry, this first number here is degrees. And so I should have my little degree symbol everywhere that I'm supposed to have it. And then you simply divide that by 60. You get 43,200 degrees per second. We're going to apply essentially the same strategy in B, except this time we're talking about radians. So we take our 7,200 revolutions, We times it by the number of radians to complete one full revolution, which is 2 pi, which gives us 14,400 pi radians in 1 minute. And then we take that number in our angular velocity formula here, 14,400 pi radians, and we divide it by 60 seconds, and we end up with 240 pi radians per second. Okay, whenever we can, we're going to express radians in terms of pi. So sometimes when you're on your calculator will round your answer right away. So if you were doing this on your calculator, you would just do the numeric part. You just do 14,400 divided by 60, and then remember that you still have a pi in the numerator. Then you'll get the exact answer. All right, if you flip the page, you see a blank unit circle. You get to practice your coordinates again, which is the sine and cosine at each angle. But really the key is inserting the radian measures in the middle there instead of the degree measures. So work yourself around the circle. You already know that over here you have 0 degrees and 0 radians, okay? And over, if you go all the way around, you have 2 pi radians. Okay, you don't need to write rad each time, just write the actual measurement. So all the way over here you have 0 and 2 pi, which means over here is 1 pi. And I'm going to allow you to try your best to fill in the rest. Practice problems are at the bottom. They come from page 208 in your textbook.